In the last video, we established that horizontal scaling, adding more servers, is how the internet handles massive traffic. But here's the immediate question. If you have 10 servers, how does a user request know which one to go to? That's the job of a load balancer. It's one of the most fundamental components in any large-scale system, and it comes up in virtually every FAANG system design interview. Today we'll cover what load balancers do, the algorithms they use to distribute traffic, the different types, and the advanced patterns you'll need to know for senior-level interviews. Without a load balancer, users need to know the IP address of a specific server. That creates three problems. First, you can't scale. If you add a new server, users need to be told about it. That doesn't work at internet scale. Second, you have no fault tolerance. If that server goes down, users are stuck. They have no other server to try. Third, load is uneven. Some requests are cheap, some are expensive. Without routing intelligence, one server might be doing 10 times the work of another. A load balancer solves all three problems by sitting in front of your server pool and acting as a single entry point. Think of what this abstraction actually gives you. From the user's perspective, your system has one address. Behind that address, you can add or remove servers, deploy new code, drain traffic from a server for maintenance, all without the user noticing. The load balancer is the seam between the outside world, which sees one system, and the inside world, which is a fleet of machines. That seam is enormously valuable. Every major application you use relies on load balancers. When you open Instagram, your request hits one of Meta's load balancers before it reaches any application's server. When you do a Google search, the load balancer in front of Google's front-end tier decides which of thousands of servers handles your query. This is infrastructure so fundamental that most engineers take it for granted, which is why interviewers probe it so specifically. Load balancers use different algorithms to decide which server gets each request. The choice of algorithm matters a lot. It affects performance, fairness, and system behavior under different load patterns. Let's go through the main ones. Round robin is the simplest algorithm, and often the default. It works well when all your servers have identical hardware, and all requests take roughly the same amount of processing. But what if server 1 is handling a heavy video transcoding job, and server 2 is idle? Round robin will keep sending requests to server 1 regardless. That's suboptimal. There is also a weighted round-robin variant. If you have heterogeneous servers, say, one server with 32 cores and two servers with 8 cores each, you assign weights proportional to capacity. The 32-core server receives 4 times as many requests as each 8-core server. This is common in mixed fleet deployments where you're transitioning between hardware generations and cannot replace all servers simultaneously. Least connections is more intelligent. It tracks how many active requests each server is currently handling and routes new requests to the least busy server. This works much better for workloads with variable request duration, like video streaming, file uploads, or long-running API calls. There's also a weighted variant of both round-robin and least connections. You assign weights to servers based on their capacity. A server with 32 cores might get a weight of 4, while a server with 8 cores gets a weight of 1. Requests are distributed proportionally. Least connections is the right default for most production web workloads. The overhead of tracking active connections is negligible. The load balancer already maintains those connection tables. And the payoff in preventing server overload during request spikes is significant. IP hash, sometimes called sticky sessions, ensures a given client always reaches the same server. This is useful when your application stores session state locally on the server. Note: the better architectural choice is to make your servers stateless, as we discussed in the previous video. But IP hash is a pragmatic solution when you're working with legacy systems that haven't made that transition yet. There is a more sophisticated variant called consistent hashing, which we will cover in detail in its own video later in this series. Consistent hashing is how distributed caches, like memcached cluster, decide which node holds a given key. It solves a harder version of the same routing problem with much more elegant properties when nodes are added or removed. Load balancers don't just distribute traffic, they also monitor the health of your servers. Active health checks work by periodically sending a lightweight request, often an HTTP GET, to a health endpoint to every server in the pool. If a server stops responding or responds with an error, the load balancer removes it from rotation. New requests stop going to it. When the server recovers, health checks detect that too, and it's automatically added back to the pool. This is the mechanism that gives load balancers their high availability superpower. A server can crash at 3 a.m., and the load balancer will route around it, with no human intervention needed. The health check endpoint itself deserves careful design. A naive implementation returns HTTP 200 as long as the process is running. But what if the application server is alive, but its database connection pool is exhausted, or its upstream dependencies are timing out? A well-designed health check endpoint, often at health or ready, validates that the server can actually serve requests end-to-end, not just that its process is alive. There is a distinction worth knowing. Liveness checks determine whether a server is alive at all. Should the load balancer remove it from rotation, while readiness checks determine whether a server is ready to accept new traffic, should the load balancer send it new requests. Kubernetes exposes both separately. A server might be live but not ready, for example, during a warm-up period after a restart when it is loading caches or establishing connections. There are two major types of load balancers, distinguished by which layer of the network stack they operate on. A Layer 4 load balancer operates at the transport layer. It makes routing decisions based on IP addresses and TCP/UDP ports. It doesn't look at the content of the request. It's extremely fast and efficient. A Layer 7 load balancer operates at the application layer. It reads the actual content of HTTP requests, the URL path, headers, cookies, query parameters, before deciding where to route. This enables much more sophisticated routing rules. Layer 7 load balancers are what most modern applications use. They enable patterns like route all requests to API to your API servers, but route requests to jar static to your CDN or object storage. This is not possible with a Layer 4 load balancer. They also handle SSL termination. The load balancer decrypts HTTPS traffic and forwards plain HTTP to your backend servers. This means your backend doesn't need to deal with encryption, which simplifies configuration and improves performance. SSL termination at the load balancer also means certificate management happens in one place. Instead of managing TLS certificates on 50 backend servers, you manage one certificate on the load balancer. When it expires or needs rotating, you do it once. Layer 7 load balancers are also where canary deployments live. You can configure rules like route 1% of traffic to the new version of your service and 99% to the old version. Monitor error rates. If the new version looks good, gradually shift more traffic. If error rates spike, shift back immediately. This is how Netflix and Amazon deploy code changes. Not big bang releases, but gradual traffic shifts with automated rollback. The trade-off is performance. Because Layer 7 load balancers inspect packet content, they do more work per request than Layer 4. In practice, modern software load balancers like NGINX and HAProxy handle millions of requests per second even at Layer 7. This is rarely a bottleneck in practice, but it is worth knowing the theoretical difference. Here's a question worth asking. If the load balancer itself is a single machine, isn't it a single point of failure? Yes, it is. Which is why production systems almost always run load balancers in pairs, active-passive or active-active configurations. In active-passive, one load balancer handles all traffic. The other sits idle, waiting. If the primary fails, the secondary takes over using a technique called IP failover. It assumes the same virtual IP address and traffic resumes in seconds. In active-active, both load balancers handle traffic simultaneously. A DNS layer rotates between them. If one fails, the other absorbs its traffic. At cloud scale, managed load balancer services, AWS application, load balancer, Google Cloud Load Balancing, handle this redundancy invisibly. They run behind anycast IP addresses, meaning traffic is routed to the nearest healthy load balancer node in a globally distributed fleet. There is no single load balancer machine to fail. The fleet is the load balancer. For on-premises or hybrid architectures, HAProxy and NGINX in active-passive pairs using keeper-lived for VRRP, Virtual Router Redundancy Protocol, is the standard pattern. Failover happens in under a second when the primary goes down. Load balancing is one of the most reliably tested components in system design interviews. Here is how to handle it correctly. When you first sketch a horizontally scaled architecture, always draw a load balancer in front of your application tier, even if the interviewer hasn't mentioned it. Adding it without being asked signals that you understand stateless horizontal scaling as a default, not an afterthought. When the interviewer probes your load balancer, you want to be able to answer 3 specific questions cleanly. First, which algorithm? For most interview scenarios, least connections is the right default answer for application servers. If the workload is strictly uniform, identical hardware, similar request cost, round robin is acceptable. If you have stateful legacy servers you cannot change, mention IP hash and then proactively say you would prefer to externalize the state instead. Second, Layer 4 or Layer 7? The answer is almost always Layer 7 for a modern web application because you want URL-based routing, SSL termination, and canary deployment capability. Be explicit. I'd use an L7 load balancer because I need to route API traffic differently from static, and I want SSL termination at the edge. Third, how is the load balancer itself made highly available? Either describe an active-passive pair with VRRP failover, or simply say, in a cloud deployment, I'd use the Managed Load Balancer Service, AWS ALB or GCP CLB, which is intrinsically highly available. That is a complete and correct answer. One more thing interviewers look for at senior level. Where do load balancers exist in the stack? It is not just between users and application servers. Internal load balancers sit between service tiers in a microservices architecture, between your API gateway and your downstream services. Each service tier has its own load balancer. Mentioning this shows you understand production-scale distributed systems, not just the entry point pattern. These are the load balancer benchmarks that will make your scale estimates credible. NGINX, Running as a Layer 7 HTTP proxy on a single modern server handles 1 to 2 million HTTP requests per second. HAProxy benchmarks are comparable. These numbers are so high that in virtually all interview scenarios, the load balancer is never your bottleneck. Your database is. State this explicitly if asked. The load balancer can handle our full request volume comfortably. The bottleneck is downstream. Layer 4 load balancers, which do not inspect packet content, can handle 10 to 40 million packets per second on commodity hardware. AWS Network Load Balancer, which operates at Layer 4, handles millions of requests per second with latency under 1 millisecond. Load balancer latency overhead. A well-configured Layer 7 load balancer adds under 1 millisecond of latency, typically in the range of 50 to 500 microseconds. For context, a database query on a warm index takes 1 to 10 milliseconds. The load balancer is not the latency problem. Health check frequency and failure detection. Most production configurations run health checks every 5 to 30 seconds, with a failure threshold of 2 to 3 consecutive failures before removing a server from rotation. At a 30-second interval with a 3-failure threshold, a failed server is removed within 90 seconds. For tighter SLAs, reduce the interval to 5 seconds. Failed server removed in 15 seconds. SSL termination throughput. Hardware SSL acceleration can handle 50 to 100,000 TLS handshakes per second. Software-based termination on modern CPUs using AES-NI hardware acceleration handles 20 to 30,000 handshakes per second per core. This matters at very high connection rates. A flash sale causing millions of simultaneous new connections will stress your TLS stack before your HTTP stack. AWS Application Load Balancer scales automatically and has processed over 1 trillion requests per day across all AWS customers. This is not a number you cite in an interview. It is context that tells you managed cloud load balancers are not something you need to worry about sizing. Load balancers are the traffic directors of the internet. They distribute requests, monitor server health, and enable the kind of horizontal scaling that powers every major application you use. The key algorithms are round-robin for uniform workloads, least connections for variable workloads, and IP hash for session affinity. Layer 7 load balancers give you content-based routing and SSL termination, and the load balancer itself must be made highly available through redundant pairs or managed cloud services. In the next video, we tackle caching, the single most powerful tool for improving system performance. If load balancing is about distributing work across servers, caching is about eliminating work entirely. Instead of computing the same expensive result a million times, you compute it once, store it, and serve it from memory. Cache hit rates, eviction policies, invalidation strategies, and the failure modes that trip up engineers in interviews. All of that in video 4. Subscribe and see you in video 4.